All right, so we're going to pick it up where we left off last time with our discussion about limits. Before we do that, I just want to quickly remind you some of the key properties that we saw last time. For example, the limit of a constant equals k, no matter what x approaches. We know that x to the n power, the limit of x to the n power is simply equal a to the n power. Now, what we're actually doing here is simply replacing the x with the a. So as long as this does not result in either division by zero or an imaginary number, we just go ahead and directly substitute a into x and see what we get. So all polynomials are going to be solved in the exact same way. In other words, it's just going to be a string of x's to different powers plus a constant. And so for the most part with polynomials, we're just going to solve the limit with direct substitution. Just like this one, the limit of x squared as x approaches 3 is simply equal to 9. And again, that's because this is not going to lead to division by 0. There's no discontinuities in this function. And so we can just directly substitute and we'll have our final answer. Now, algebraically, if we have the limit of some constant times a function, we can factor out the constant and then focus our attention just on solving that limit. Sometimes this will be quicker and easier than trying to do the whole thing, especially if it's a very messy expression. So a lot of times these rules will help us take an expression that is very complicated and break it down into simpler pieces so that we can evaluate it more easily. Now here, for example, we had the limit as x approaches a of k x to the n. So now here we didn't even bother to factor out the k. It was so simple, we just replaced the x with an a. So we end up with k a to the n power. We also saw that the limit of a sum is equal to the sum of the limits. We also saw that the limit of a product is equal to the product of the limits. And finally, we saw that the limit of a quotient is equal to the ratio or quotient of the individual limits, as long as the denominator is not equal to 0. Okay, in other words, if that limit in the denominator gives us a 0, then we can't use this rule directly, although as it turns out, there may be ways to get around this. Okay, we'll see that under some conditions, even if the denominator is 0, we might be able to still find the limit. So this is a very unusual situation where division by 0 is something that doesn't necessarily stop us in our tracks, but it means that we have to try something different. All right, I think, and then the power, of course. This is directly follows from the power rule that we saw with derivatives, or not derivatives, with algebra. And so now we can move on and take a look at some more examples where we're going to combine some of these rules, and that will enable us to solve progressively more complicated limits. Okay, so like this first one is very straightforward. It is a polynomial, and because it's not possible for this to result in division by 0, we can literally just directly substitute the -3 in for x, and then we can solve. So all you have to do is replace the x with -3, and you're done. By the way, if you want to see how this would look on a graph, symbol right here. And if you look at it now, of course, you can see right away that this is nothing but a straight line, a positively sloped straight line. So if you look at this graph, we're looking for the point where x approaches -3. And so if you find -3 over here and read down to the line, you'll see that the corresponding value of y is -10. And by the way, if you notice, that's going to be true whether we're approaching -3 from the right or from the left. All right, so in a case like this, the limit is very simply the value of the function at that point. That's all it is. And in turn, that will always be the case with polynomials. Now, if you wanted to, you could use the rules that we learned before and break this up into individual terms that can be evaluated separately That wasn't really necessary here. You can see, for example, we turned it into the sum of limits, and then here I factored out the 4 before doing any substitutions. And here you can see that this is the limit of a constant, which is just equal to the constant. But we ultimately, of course, end up with the same result, -10. We have to. So then when would you ever break up your limit into smaller terms like this? Only if it simplifies things for you. Right? So, I mean, you don't know when that's going to happen. In a case like this, it's not that important, but there may come times when using the rules will make it a lot easier for you to calculate your limit. Now here, we do have a quotient. So when we have a quotient, the first thing we have to ask ourselves is whether or not this limit could result in division by 0. And here, fortunately, the answer is no. Okay, so that means we can just go ahead and directly substitute 2 for x. And we'll end up with the correct result. Okay, so what do we have? We have 2 times 4, which is 8 minus 6 plus 1 over 8 plus 4, or 2 plus 1 over 12, 3/12, or just 1/4. Now, again, we could actually just throw this into Symbolab. Oh, let's do that just to see. I'm not sure what this thing looks like, but let's give it a shot. All right, so we have the ratio. Was it 2x squared minus 3x plus 1 divided by x cubed plus 4. And what we're really interested in is seeing what happens when x equals 2. Okay, so let's take a look. Oh man, it must be a very messy function. Look how long it's taken. Yeah, once in a while it runs into trouble. Unless my computer is unbelievably slow tonight, which is also possible. There we go. All right. Okay, now this is weird. It's not offering. Oh, there it is. Look at this thing. Now I have to tell, I see, this is what I mean. You never know. Some of these things are, these functions are so bizarre, but we're looking for the function, the limit as x approaches 2. So we can kind of zoom in on this part of the graph. And you can see, I mean, this is 2, and this is approximately a quarter. Yeah, right there, right across is 1/4. Okay. So that is exactly what just happened. This is probably why it took so long to come up with this graph. Imagine Symbolab saying, "Are you kidding with this thing?" It is kind of weird looking. All right, now, but again, here I've broken it up using the rules, and you can see that this didn't really help us very much. So this isn't really necessary, but it does at least remind you how the rules work. So you don't have to feel like you must do this, all of this. As long as it's clear that you're not going to cause division by 0, you can just go ahead and substitute for all the x's and come up with your answer. Now, this one looks at first glance to be a nightmare, but see, here's where the potential exists for problems. If we end up with a negative square root, then we have a real problem, because we only want real numbers here. But as you can see, that's not going to happen. So therefore, we can go ahead and substitute 2 times 6 minus 1 radical 6 plus 4. 12 minus 1 radical 10, or simply 11 radical 10. And you can't actually simplify it any further. That's as far as you can take it. So let's just leave it like that. Now, of course, if you need the exact value, that's a different matter. You can go to your calculator and come up with an approximate value for 11 radical 10. It'll be about 35 or so. All right. Now, we're going to be looking now at rational. Now, remember, rational means a ratio, a function that is itself a ratio of two other functions. Now, here you can see where we can potentially have issues if this a causes this function q to go to 0, then we have to do something different. Either that or the limit is undefined. So let's look at this case. Now here, once again, we got lucky because substituting 0 here will not cause division by 0. So once again, we have a very simple case. Even though it's a ratio, we don't have to worry about division by 0. And you can see all the terms cancel out except that 5 and the 4. So I think we don't need to go look at symbol lab for this one. It's clearly going to be a very messy function, but it will have when x goes to 0, it'll be 5/4. In other words, the intercept will be 5/4. All right, now what happens though if we do have division by 0? Now, when any other situation you've ever run into, normally when you have division by 0, you just have to stop it. You're done. But here it turns out that there may be ways we can still find a limit, even if we have a ratio with a 0 in the denominator. We're not going to, we're going to see a couple of different ways of working with this type of situation, but not necessarily right away. Some of these have to wait till a later chapter. But anyway, what we want to do here is note that for any two functions that have the same value for all values of x except possibly a, and they must have the same limit as x approaches a. Okay, now what exactly does that mean and why is that relevant? Okay, well, we're going to find out. Let's take a look at this case. Now, for the first time here, you can see we have a problem. If we replace these x's with 1, we're going to have not just division by 0, but we're going to have 0 over 0. Oh no, what do we do now? So I'll tell you what, why don't we look at this one on Symbol Lab, just so we can visualize what's happening here. Let's see. So we have x squared minus 1 over x minus 1. All right, let's look at the graph. Oh, I know. You know what I forgot to do? And you always have to hit the go button so it understands that this is the function that we're talking about now. So, yeah, there we go. So the point of interest here, we're trying to find the limit as x goes to 1. Now, what do you notice here? Oh man, what's going on? Okay, so what I wanted you to notice is that when x equals 1, there's a hole here. That normally would be the point 1, comma 2, but this function is actually undefined at that point. On the other hand, if you notice, as x approaches 1 from the left, we're getting infinitesimally closer to 2. And the same thing is true when we approach x from the right. So that is an important clue as to what's about to happen. Now, what we're going to do here is notice that we can actually simplify this function, because x squared minus 1, it turns out, is equal to x plus 1 times x minus 1. And you can figure that out with factoring, or you could try the quadratic formula, but you can double check that with FOIL. All right, here's f. X squared, the outer terms are these two. Negative x, the inner terms are these two. Positive x. And then these are, the last two terms are these two. These cancel each other out. And then we do indeed end up with x squared minus 1. So what that means then is this thing reduces to x plus 1. And then all of a sudden, sorry. All right, actually, I'll tell it. Let me write that on the next slide so you can read it better. So what that means then is the limit of our original function now that's important, because if you notice here, this is clearly equal to 2, because I'm just substituting 1 in for x. So you're probably wondering, well, why does that suggest, or what does that do for us? Well, what you have to do is visualize. You've got two functions going on here. This function is this straight line with a hole in it at 1, comma 2. The function x plus 1, I'll try to draw it in red here, is the exact same thing except for that one point. So the key here is that they're equal to each other except when x equals 1. Therefore, the limit of the first function when x approaches 1 equals the limit as x approaches 1 of x plus 1. That's what that theory was telling us. In other words, as long as they are equal to each other for all x's except that one, then they must have the same limit at that point. And that's exactly what happened here. Okay. So that implies that this original function that we started out with must have a limit of 2. Because this equivalent version of it, meaning that it's the same everywhere except at x equals 1, has a limit of 1, which means they must both have a limit of 2. So there you go. So you now have this function with a discontinuity in it, and yet we still have a limit. And like I was saying, you could tell because if you look at it carefully, you'll see, let's go back to the graph. The giveaway here is that as you approach from the left, y is getting really, really close to 2. As you approach from the right, y is also getting infinitely close to 2. So therefore, right here, that's your limit. Okay, but we have to, prove it formally. So anyway, this is one of the tricks we can use to come up with a limit, even if there is division by 0 or some other kind of discontinuity. And it's not the only way, by the way. There's other ways we can get around this problem. Well, that was interesting. And then, what about the really special case? This is sometimes called an indeterminate form. There's a few of these. 0 over 0, infinity over infinity is another one. When you run into a case like this, again, there may be techniques we can use to find a limit. Okay, so we shouldn't stop and say, well, listen, we're done. That's all over. There might still be a limit. Okay, so like here's another example of this. So we know, it's a polynomial. We can plug in the 3 for all the x's. But if we do, look what happens. What do we have? 9 minus 9 over 18 minus 15 minus 3. Yeah, there we go. 0 over 0. Oh, now what are we supposed to do? Well, one thing we're not going to be able to do, if you notice, the numerator and the denominator are both quadratic expressions. So there's not going to be any factoring here. What else could we possibly do? Oh, wait a minute. My mistake. There is factoring, but it's a very interesting kind of factoring. Now, again, this is the kind of thing that you might not notice it right away, but yeah, it wasn't that obvious at all. Let me just write out on a new slide what just happened here. You've got x hold on a second. Yeah, I was a little surprised to see that myself. It turns out that x squared minus 3x over 2x squared minus 5x minus 3 can be simplified. I think the trick here is to notice that the numerator could be written as x times x minus 3. So what you might want to do is look at it and say, listen, is it possible that x minus 3 is also a factor of this denominator? And one way you can check it is with something which is sometimes called synthetic division. It's like long division. And what are you actually trying to do here? Well, let's see. If I multiply x minus 3 by 2x, I'll get 2x squared minus 6x. Now I'll subtract this entire expression. These drop out. This becomes positive 6. Well, what do you know? So what this means, what I've just shown you, is that x times x minus 3 is now divided by x minus 3 times 2x plus 1. And if you're not sure, you can confirm this with the FOIL method. So what you've actually got here, then, because these cancel out, is x over 2x plus 1. And now we can take this limit And let's see what we get. We have the x equals 3. See how easy this becomes. You'll have 3 over 2 times 3 plus 1. 3/7. So once again, we're using that same rule. I mean, these two, the original value we had, x squared minus 3x divided by 2x squared minus 5x minus 3 equals x over 2x plus 1, except when x equals 3. Why? Because then the first one has a discontinuity. So that implies that they must have the same limit when x equals 3. And so therefore, I can find the limit of the first one, the first expression, by taking the limit of the second expression. And here I can just easily substitute 3 and I come up with the correct value. Very good. All right. So in other words, what they're basically telling you here is that when you have a complex expression and you think that you're going to have a problem with direct substitution, the best strategy is to try to simplify as much as possible. When there are ratios involved, often factoring is the best approach. For other situations, well, that's, we'll treat those on a case-by-case basis. Now look at this one. Now we're going to have a slightly different approach this time. -1, the limit as x approaches -1, clearly I'm going to end up with a problem here. So this is radical 1. And I ended up with 0 over 0. Oh my God, what am I supposed to do? All right, now, we can look at Symbolab for a second here. I'm not sure what this thing is going to look like. It's, was it radical x plus 2 over 1? And then down here we have x plus 1. Okay, in about a minute, it's going to offer me a graph. Yeah, I guess it's a very strange graph. It doesn't act like this when we have straight lines and parabolas. Ah, okay. Oh, even then we have to wait for it to offer us a graph. See, now that doesn't look that strange. But we're trying to find the limit at -1. There we go. I almost didn't see it there. There's a discontinuity there. And even it helps us out by showing us that at -1/2. So we need another function that is identical to this one everywhere except where x equals -1. Whatever its limit is the limit of this function as well. How do we find it, though? Now, this is something that you might have forgotten about. We're going to do the following. You might remember this concept of conjugates. because it's the same radical, and the same constant. It's just that one is plus and one is minus. In fact, maybe what we should do is look up a formal definition. Now, okay. I guess I should have been more specific. A pair of binomials with identical terms but parting opposite arithmetic operators. In other words, it's more general than what we're seeing here. In other words, what they're suggesting here is that it doesn't have to be square roots. So, for example, radical 3 plus 3 plus radical 2, the conjugate of that would be 3 minus radical 2. We often see this with imaginary numbers. Like here, for example, 3 plus 4i, its conjugate is 3 minus 4i, although then when we have a case like that, we typically refer to it as a complex conjugate because those are both complex numbers. But the word conjugate essentially means two terms where they're only different by the sign. Okay. So why does this matter? Because watch what's going to happen now. If you take this messy expression, we can't factor it, but what we can do to try to simplify it at least is to multiply the entire expression by a ratio, which is clearly equal to 1, where these are conjugates of each other. Now, the only motivation for doing this is to hopefully simplify this so that we can find an expression where we can directly substitute x equals minus 1 without leading to division by 0. Okay, so remember, we're searching for another function that is identical to this one, except at this point, x equals -1, and then we can take our limit. So, by the way, yeah, conjugates, it simply means they're, and by the way, they have to be binary terms. That means there's two components. Two things are either being added together or subtracted from each other. And you can see all of these pairs are conjugates of each other because, again, the only thing that's different is the sign. But there has to be two terms in each one. So anyway, let's see what happens when we algebraically, let's see what happens here. All right. Now, this is going to be a bit of a mess. I'll give you that. But it might just do the job. So, we can apply FOIL in these cases. So let's do the numerators. Oops. And so if we apply FOIL, remember, it's not the numerator that we're worried about, it's the denominator. We really want to avoid having x plus 1 down here. So here the first two terms are these two. Now, if I multiply radical x plus 2 times radical x plus 2, I'll just end up with x plus 2. The outer would be this one. The inner would be this one, which is negative radical x plus 2. And the last would be -1. By the way, the good thing about these conjugates is that when you multiply them together like that, the outer and the inner terms are guaranteed to cancel each other out. And that's, again, one of the reasons why we're doing this. So it means the numerator will simplify to x plus 1. Very good. Now, what about the denominator? This is the one we were worried about. We don't want division by 0. So here in the denominator, we have first we have x plus 1 is multiplied by radical x plus 2 plus 1. Again, let's try FOIL. Oh, actually, no, you notice how when I said before that these are guaranteed to cancel out, that's only when they're conjugates of each other. It's only the numerator where we have conjugates of each other. In the denominator, anything could happen. Okay, so I didn't want to confuse you. We multiply the numerator. In the numerator, we have two conjugates, which guarantees that the O and the I will cancel out. Not so in the denominator. Anything can happen here. Okay, here we go. First, x times this. O is here. I is here. Last is these two. So you've got two terms that are functions of x, radical x plus 2. So I can actually streamline this by rewriting this as x plus 1 times radical x plus 2 plus x plus 1. So you're probably wondering, well, how did that help us? So here's what's happening. The original expression we had so for this one, we have in our numerator, we just got through showing that the numerator is just x plus 1. And the denominator is x plus 1. Ah, well, this is interesting. I didn't even notice this. Ah, so in other words, look what's going to happen. Because I've got the same term, x plus 1 times radical x plus 2 plus x plus 1. These will drop in. So now we're getting somewhere, because remember, we're still trying to take the limit as x approaches -1, and all of a sudden our problems disappear, because when we take this limit, okay, we're going to end up with direct substitution. One half. So that is the limit of our original function, 1/2. Now you could tell by looking at this graph, by the way, that it was going to be a half, because that is where the discontinuity is. In other words, what we essentially just did was say, listen, let's find another function which is the same everywhere except at this point. And here, that point, in effect, is filled in with 1/2. Okay, so in other words, it's the equivalent function where this discontinuity does not exist. So ultimately, we have a limit of 1/2. Wow, that was a lot of work. So you can see we started out with some polynomials and we were thinking, wow, this is going to be a breeze. And all of a sudden, it got really complicated in a hurry. Well, wait till you see the next one. Oh, it's not that bad. All right, so here we go. So obviously, right off the bat, you can see that substituting 1 is going to give us 1/2 minus 1/2 over 1 minus 1, 0 over 0. So this is once again an indeterminate form. So we're going to try to figure out how to essentially simplify this. Now, we may be able to consolidate the two terms in the numerator and then maybe do some factoring. So let's try that. Okay. That looks like it's a possibility. So actually, let me copy the original equation real fast. And you're starting to notice that, there's going to be several cases that we potentially run into. So you have to start to develop a talent for figuring out what possibly we could do to simplify our results. So why don't we take this and try to figure out what to do with it? We need a common denominator. So here's what we're going to do. So basically what we're going to do is multiply the first term by 2/2, because we have 2 here, and the second term by x plus 1 over x plus 1. That is one way to guarantee that we'll have a common denominator. It doesn't guarantee that we're simplifying anything, but it's guaranteeing us a common denominator. At the very least, we can consolidate these two terms. So whatever is in the numerator, we have 2 times x plus 1. And so we're going to have all right, so 2 minus x minus 1. And then I guess here we can just write this out. How does that help us? Well, let's see. So once again, I'll quickly remind you what the original function was. And then we'll write in there the this expression we just developed for the numerator. All right, now we're going to have to get clever here. The numerator looks like this. The denominator could be rewritten as negative 1 minus x. Let's see. Now let's do this. I'm going to rewrite it slightly differently. You'll see why in a minute. So I'm going to copy this to the next slide. Now, I just want to quickly remind you, here's an important property of algebra. A over B over C over D is the same thing as A over B times D over C. Okay, so we have, for example, 3/4 over 7/8, it would be the same as 3/4 times 8 over 7, which is 24 over 28. So that means here I'm going to have 1 minus x over 2x plus 1 times 1 over negative 1 minus x. Now, if you can write this x, this negative in the numerator if you'd rather. The reason why I might want to do that is because I want it to be crystal clear that these now cancel out. And so our original messy function is going to be reduced to this. And so now I can easily take the limit. Remember, originally the limit was supposed to be of 1. Oh, I think I may have made an algebraic error here somewhere. Oh, I see what it is. I don't know what happened. All of a sudden, Jesus, what happened? I just copied it wrong. Okay, those were supposed to be twos. I don't know how I could have done that. Yeah, that was the whole problem right there. All right. So the final answer is negative 1/4. Whoa. So the basic logic hasn't changed. I mean, really, all we're doing is taking a function whose limit cannot be evaluated directly due to division by zero and rearranging it algebraically to find something that we can substitute directly into. And each case can be different. So we have to be very, very careful here. Now, I am pretty sure that Symbolab is capable of doing this. In fact, why don't we give it a shot? I want to see how it reacts to this. So there's a limit here. As x goes to 1, and the original function was, okay, here we go, 1 over x plus 1 minus a half all divided by x minus 1. All right, take it away, Symbolab. Yeah, negative a quarter. So, it very helpfully gave us a graph too. So at x equals 1, there it is, negative a quarter. All right, now it does offer, now, the thing is, I have a subscription to this thing. So I'm not positive it will show you all the steps if you're not paying for it. Because I do, I mean, it's not very much money. I have it because I might need it. But yeah, well, it did simplify it for us though. And then it did, yeah, okay, so it's showing you what you need to know. All right. Oh my God, there's another one. All right, well, you know what? Here's the thing. We need the practice. You might start to say, you know what, we're getting tired of this. No, you can't have enough practice with math. All right. In fact, all right, the first thing you do is observe directly that direct substitution is going to give us a problem. Okay, because we'll have 1 over minus 3 plus 2 plus 1, or minus 3 plus 3. And there you go. All right, so what do we do? Well, I think it's going to be very much like the one we just did. We're going to have to figure out a way to consolidate those two terms in the numerator. So let's try this. So here's my idea. For the numerator, let's rewrite one as x plus 2 over x plus 2. Oh, this one won't be too bad. Because all you're going to have then is 1 plus x plus 2 over x plus 2. Oh, even better. You're going to have x plus 3 over x plus 2, all divided by x plus 2. And I'd like to write it like this so that I can clearly show. Oh, all right. Well, you know what? Even I was hoping we could get some cancellations here, but it doesn't matter. I'll tell you why. Because we were originally trying to take the limit where x equals -3, and now that's not a problem. So even though it didn't really simplify that much, at least we're not ending up with division by 0. And you can see it actually just ends up being 0. And that's possible. The limit can be 0. Oh, you know what? I just realized it must be getting late. I just realized that I goofed it up right here. This was actually 3. No, this was supposed to reduce itself. Sorry. The numerator part is correct. I just copied it wrong again. Let's try that. So up to this point, it's fine, but I just noticed, yeah. Now, yeah, it was supposed to simplify. So remember the way I wrote it earlier, so dividing by x plus 3 over 1 is equivalent to multiplying by 1 over x plus 3. Yeah, these do. And now it's just -1. That's better. Okay. Now, okay, there's one more example here. And then what we're going to do is we're going to start considering the idea of evaluating what are called one-sided limits. In other words, sometimes we only need to know what the limit is as we approach from one direction or the other. It's not always the case that we need a two-sided limit. It depends on what situation we find ourselves in. For example, it may be that only one of the two makes sense because of the application that we're looking at, but it is possible to evaluate a one-sided limit. But before we do that, we have one more example. Let's see, this one. Now, again, as we've been seeing all this time, direct substitution is going to be a problem. Well, actually, it's just no. Okay. So let's see what we can do with this. Now, of course, we're going to need a common denominator. One over x plus 5 over x times x minus 5. Let's try multiply this by x minus 5. So we'll have x minus 5 plus 5 over x minus 5. Well, that worked out well because when we take the limit, oh, man, that was kind of nice. Negative 1/5, and that's it. So it was easier than usual to find a common denominator. That's why that worked out so nicely. All right. Now, let me just show you quickly where we're going with this. Now, this is still section 2B. Let me just take a quick look at what's going on in 2C real fast. Ooh. We're going to have some more theoretical discussions here, and we're going to get some really peculiar results here. Wow. Now, once this discussion about limits is over, we're going to move into really maybe one of the most important topics in all of calculus, which is derivatives. So the reason why we're doing this order is because derivatives are defined in terms of limits. So you have to understand how limits work before you even attempt to do derivatives. But once we start them, you'll see that they're actually surprisingly straightforward for the most part. And it is really, I mean, if you're going to use one technique in calculus more than all the others, this is the one, derivatives. Most of the results you'll see going forward are based on derivatives. And there's so many real world applications of them. So we're going to wrap this up fairly quickly so we can dive into the derivatives. Now, the only issue with derivatives is that there's many cases we could encounter. So there's many different rules you'll have to be exposed to. But once you practice a little bit, it'll start to become second nature. So anyway, let me just quickly show you what's going on with one-sided limits and why you might be interested in this. Because let's look at something like this. Yeah, now here, the problem here is that -3 is going to give us an imaginary number. So we can't obviously evaluate this directly. So we have to do something a little different. So we'll see what that is next time, I guess. And so we'll wrap it up with one-sided limits, and then we'll look at some theoretical discussions. And then when that's done, we can then go ahead and start, like I said, probably the most important topic of the semester, which is derivatives. Okay. All right. So I'll see you all next time.